All right, welcome back, everybody. So we're going to look at some examples from 4.3, which was where we used the limits of a Riemann sum, and then we defined the definite integral. So the main idea for 4.3 was that the limit as n goes to infinity of the sum of I equals 1 to n, f of x delta x, f of x sub I delta x. We added this new notation of the integral from a to b of f of x dx. And again, what this is describing is some curve over a closed domain. And we calculated the area underneath that by taking n rectangles, or n geometric areas. So as we let the number of rectangles approach infinity, it shrinks down and becomes more and more accurate until it gives us the exact area. So this was our exact area under F. And so is this. So these are equivalent statements of each other. Now, the main idea is to get the definite integral as an understanding so we can compute faster. But we still need to use this limit of a Riemann sum in kind of a theoretical framework just to show our understanding of what it represents. So for 4.3, there were kind of some common examples. So a very simple, straightforward example would be to go from the limit of the Riemann sum into the definite integral. All right, so let's suppose that we had, for our first example, so we're going to take the limit as n goes to infinity of the sum of I equals 1 to n, and maybe we have 3 plus 2i over n squared times 2 over n. So the question is, what is the definite integral that is represented here? So what we need to figure out then is what each piece is in general and see if we can figure out what the function is. So this one is kind of written not in a deceptive form. So I'll kind of show you what some deceptive forms might look like. So this is our f of x sub I here, this 3 plus 2i over n squared. And then our delta x is given here as 2 over n. And if we look, we'll note there's a delta x inside of our function there, it looks like. And that's exactly true, that there is going to be that delta x represented inside. Because remember, delta x is the width of each subinterval. And so to get from one subinterval to the next, we can just continually add delta x. So let's suppose we still don't know what our function looks like, so we're just trying to kind of generalize. So let's say that our function looks like this. And so we need to figure out, okay, where is it going to be at each point? So our first point is going to be our left endpoint, which would be x of 0. And then our right endpoint is going to be x of n. So actually we could do I is equal to 0 in this case, maybe, as a simpler representation of it using left endpoints. So, or this would be n plus 1, I guess. No, it would be n. Okay. So that means that this is equal to our endpoint A. But if I look inside, I can see what x sub I is. So note, x sub I is just that inside portion of the squared expression. So 3 plus 2i over n is x sub I, which means if x is 0, then I just have 3. So that means that my left endpoint is 3 in this case. And then if I took x sub n, I would get 3 plus 2n over n, or just 3 plus 2, and that's 5. So note, we can get the endpoints just by plugging in 0 and n for that expression. And then from there, we can see then that our f of x, our actual function itself, is this quadratic function. It's just the squaring function. So f of x sub I is just equal to x sub I squared. So that means in our definite integral, we're going to have x squared. Our delta x becomes dx as it shrinks to infinitesimally small width. And then our limits of integration are going to be 3 to 5. So the integral from 3 to 5 of x squared dx is this calculation here. All right, so then let's look at another one. So we'll have the limit as n goes to infinity. And just as a secondary note, if I let I start at 1, it would be the same integral. So it doesn't matter if it's 1 or 0, but that's just going to mean that we're using a right endpoint method. But because we're going to have an infinite number of rectangles, it doesn't matter if we start from the left or the right. So we'll have the sum of I equals 1 to n of, oh, actually, let's write it. So pi over n sum I equals 1 to n of cosine of negative pi over 8 plus pi I over n. Okay, so let's kind of rewrite it a little bit differently. So note it's not in its normal form, where it's just f of x delta x. So if I'm looking at this, note this little piece on the outside is also here because that value is just delta x. So delta x is not going to be a dependent value inside of our summation. So the I value is what has to remain inside of the sum. Pi over n is just a constant. Right? So n is just some number of subintervals that we have. It does have to stay inside of the limit, however, because the limit depends on n, but we can factor it out of the sum. So that's delta x. We can see this is going to be f of x sub I. So what we're going to get is that x sub I is negative pi over 8 plus pi over n times I. So we can see that our left endpoint A is just negative pi over 8. And then our endpoint B is going to be negative pi over 8 plus pi when I is equal to n. So that's 8 pi over 8. So we'll go to 7 pi over 8. And we subtract 1 pi over 8. So then our integral is going to be the integral from negative pi over 8 to 7 pi over 8 of cosine x dx. So this is really going to repeat itself. You might get it though where it's written as an actual summation, right? So where they actually expand the terms. So that might be something to think about as well. So an example of that might be the limit as n goes to infinity of, let's say, 2 over n times so maybe it'll be something like this, where we've got log of 1 plus 2 over n, log of 1 plus 4 over n, log of 1 plus 6 over n, adding all of those terms all the way up to the natural log of 2. So the question will be, okay, well, what is, the natural log of 3. What is the integral that's being described here? And so in this case, what you want to do is you're going to want to, so they've written the 2 over n on the outside, but what we really like to do is to get this to look like a summation symbol with sigma. So we know it's going to be natural log of 1 plus, And then to get from 2 over n to 4 over n to 6 over n, I'm going to take 2 over n times I. Right, so that'll give me my sum. So then that gives you your definite integral, which will be the integral from 1 to 3 of the natural log of x dx. And I get 3 because I've got 1 plus 2 here. So 1 plus 2 is going to give me my endpoint of 3. 1 is going to always be your left endpoint. And then the delta x, of course, doesn't matter in our definite integral representation. So this is just x sub I on the inside. All right, so now let's kind of work in reverse. So let's take, for our fourth example, let's take the integral from 1 to 3 of x squared plus x plus 1 dx. And now let's make it into the limit of a Riemann sum. All right, so now we're going to work backwards. So we'll note delta x is going to be 3 minus 1 over n, since we have n subintervals, so it's going to be 2 over n. X sub I is just our left endpoint, 1, plus our delta x times I for the ith subinterval location, wherever we're located. And then we're really kind of done here. We just need to plug x sub I in wherever we see an x. So we're going to get the limit as n goes to infinity of the sum of I equals 1 to n. So note my function is x squared plus x plus 1 times delta x, which is 2 over n. And then those x's are just going to become 1 plus 2i over n. And there's our limit of our Riemann sum. So again, the key pieces for writing your Riemann sum are just delta x, x sub I, and then knowing what f of x is, right? So we do need to know what f of x is. So let's do one more. We'll do the integral from pi over 2 to pi of cosine x dx. So go ahead and give this one a try. All right, so x sub I is just going to be, delta x. Let's start with delta x. So delta x is going to be pi minus pi over 2 over n. So we're going to get pi over 2n. Right? So slightly different looking delta x expression. You could think of it as pi over 2 times 1 over n, but pi over 2n is fine. So that means that x sub I is pi over 2 plus pi over 2n times I. So then we're going to get cosine of pi over 2 plus pi over 2n times I, and times pi over 2n. And that's our answer. So really 4.3, that main idea is just kind of going between both forms. So if you have any questions, shoot me an email. Otherwise, come by the office hours. But until I talk to you next time,